Hello everyone. What we'd like to do in this video is solve exponential and logarithmic equations. We finally have all the tools we need to be able to solve these types of equations. So what I'm going to do here first, when solving exponential equations, that's where we'll start. In this video we'll specifically be solving exponential equations. Well, for some cases we don't need to use the inverses of exponentials, or we don't need to use logarithms if we don't have to. We can use the drop the base method when possible. So for example, let's say we have 64 to the power of x, and we want that to know when that's equal to 16, let's say, to the x minus 3. Let's say we want to try to solve this equation. Well, we could try to think if we could write 16 and 64 as some number to a power. Hopefully that some number is the same. I think they're both powers of 2. 16, I think, is 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16. And 64, let's see, so 16 times 2 is 32, times an extra 2 will be 64. So this will be 2 to the 6. So in this specific equation, we don't need to use logarithms. Here, we can write 64 as 2 to the 6th to the power of x. And 16 we could write as 2 to the 4th to the x minus 3. Now we can use an exponent property. Exponent properties allow us to multiply these exponents. So this will be 2 to the 6x is equal to 2 to the 4 times x minus 3. We have like bases, so boom, boom, drop the base. We'll have that. 6x is equal to 4 times x minus 3. Now we have a nice linear equation that we can solve. How about we go ahead and distribute in this 4, and we'll get that 6x is equal to what? 4x minus 12. How about we subtract 4x from both sides? So we'll get that 2x. 2x is equal to negative 12. Divide both sides by 2. And we'll get that x is equal to negative 6. X is equal to negative 6. And we have our solution. Okay, so this was great. We could also, maybe there's another one we can do here. This was drop the base method. We can solve these type of exponential equations. Okay, maybe one more. Let's say we want to solve 10 to the 2x minus 3 is equal to 1/10. Maybe go ahead and pause the video and see if you can solve this using the drop the base method. Okay, well, I think we can write 10 and 1/10 as both as 10 to a power. We need to remember that 1/10 is the same thing as 10 to the negative 1. We have a like base of 10. Boom, drop it. So we'll get that 2x minus 3 is equal to negative 1. We can add 3 to both sides. We'll get that 2x is equal to 2. Divide both sides by 2. We get that x is equal to 1. Awesome, that's great. Unfortunately though, we won't always have such nice numbers where you can do this method. So, what do we do then? Let me show you an example. Well, what if we try to solve, for example? Let's give ourselves some more room here. Let's say we want to solve how about 3 to the 2x minus 1 is equal to 5. 3 to the 2x minus 5 is equal to 5. Let's try and solve this. Well, there's a problem. The problem is how do I rewrite 5? How do we rewrite 5 as some power of 3? This is a difficult thing to do here. Can't use the drop the base method here. So what can we do? What can we do here? Well, what we can do here is use log rules. That's what we want to do here. So what we want to do is we want to take advantage specifically of log rule 3. Log rule 3. Remember the rock star rule I've been talking about? That says that log base b, any base, of what? N to the m is equal to m times log base b of n. I can bring powers out front. So what we can do here is it would be really great if I could somehow get this exponent, or this x, out of the exponent. I'd like to get it out. Is there a tool that lets me bring it out front? Log rule 3 lets me do this. So what I'm going to do is notice that this works for any base. So I can take the log, any base of both sides of this, and that'll bring the variable out front. You could use log base 10. You could use log base 7. You could use natural log. I wouldn't use log base 7. I would either use log base 10 or natural log. Why? Because, well, for most calculators, that's all they have is log base 10 and the natural log. What do I always use? I always take the natural log of both sides. Why? One less letter. Hopefully I won't get carpal tunnel. So what we're going to do is we're going to take the natural log of both sides. We're going to take the natural log of both sides. Okay, we'll take the natural log. And now what we can do is this 2x minus 5, we can move that out front. So we have 2x minus 5 times the natural log of 3 times the natural log of 3 will equal to the natural log of 5. This is great. Now that I can get this x out of the exponent, now this is an equation we can solve. We want to solve for x here. Well, in this situation, what I would probably do is I would like to get this multiplication of the natural log of 3 off of the 2x minus 5. So what am I going to do? I'm going to divide both sides by the natural log of 3. The natural log of 3. So what we have here is these will cancel. And we get that 2x minus 5 is equal to the natural log of 5 all over the natural log of 3. We can add 5 to both sides. So we'll get that 2x is equal to the natural log of 5 over the natural log of 3 plus 5. From here you could divide both sides by 2 if you'd like. Instead of dividing by 2, I'm going to instead multiply by 1/2, just so my answer looks prettier. So here, I'll get that x, maybe I'll write it up over here. Here we'll get that x is equivalent to 1/2 times the natural log of 5 over the natural log of 3 plus 5. And here, we have our answer. This is the exact answer, and we can type this into our calculator. Okay, so let's figure out what it is. Okay, I'll show you how I'm going to type this in. So, I'm going to put a parenthesis, and I'm going to put 1 divided by 2, or you could put 0.5. I'm going to open up another parenthesis, and I'm going to write the natural log of 5 divided by the natural log of 3, close those parentheses, plus 5. Now I'm going to close this parenthesis. Okay, before I hit enter, I'm going to show you what I have in my calculator. I guess I just pushed enter, but this is what I've typed in. So we have our solution. Let's go ahead and round to 3 decimal places. Is roughly 3.232. And we have our solution. Okay, so this is great. Okay, what I would like to say here really quick is while I did take the natural log of both sides, we didn't have to take this approach. We didn't necessarily have to take this approach. It's the approach I always take. I would always highly recommend you'll actually find in pretty much every single math textbook you read, people stop using logs of different bases. Everyone just uses natural log. The reason for that is really the change of base formula, and well, there's less letters. And log rule 3 lets us have the power of bringing powers down. For fun, let me show you a different way to solve this. Let's say, what did we have? We had log, we had, what was it? It was 3 to the 2x minus 5 is equal to 5. I took the natural log of both sides because I wanted to use log rule 3 here. I mean, you could have taken log base 3 of both sides because, you know, log base 3 is the inverse of a base 3 exponential. So you could have taken log base 3 of both sides. These would cancel each other out. So we would just get that 2x minus 5 is equal to log base 3 of 5. Okay, we could add 5 to both sides. So we get 2x is equal to log base 3 of 5 plus 5. And then you can multiply everything by a half. So you get that x would be equal to 1/2 times log base 3 of 5 plus 5. Okay, so now if you want to type this into your calculator, well, what would you have to do? You would have to use the change of base formula. So you'd have to write the natural log of 5 over the natural log of 3. Here we're adding 5. And this is the same thing. This is the same thing that we just had on the board. So one thing we can do here is instead of having to, use log base 3 or try to think about what the inverse of the exponential is, you can avoid that by just always using natural log, and you can almost, in this nice situation, not have to use the change of base formula. So what am I always going to do in every single math problem that I do where I'm solving exponential equations? I'm always just going to use natural log. You can always just use natural log. Okay, so what I would like to write up here before we start doing more examples is just a general strategy. It's just a general strategy for solving exponential equations. So strategy for solving exponential equations. Okay. Now this isn't going to be a strategy that works for every single exponential equation, but for a majority of exponential equations, this is kind of the strategy you're going to take. First, you're going to isolate an exponential on one side or both sides. So it depends. You'll see what I mean here in a second. Isolate exponential on one side. So at least on one side of the equation, you need to have an exponential isolated. Okay, 2, you're going to take the natural log of both sides. Take ln of both sides. You also could take log of both sides, but that's one extra letter you have to write. Take natural log of both sides and use log rule 3. Okay? Third step, what are you going to do? You're going to solve for x. So this is a strategy I always try and use when I'm solving an exponential equation. Okay, this is just a general strategy. It won't work for every single one, but this is one you should think about. Okay, I'll show you some more difficult examples at the end of the video. And it all comes down to basically you isolating an exponential, taking the natural log of both sides, using log rule 3, solving for x, or for whatever variable we have. Okay, so let's say, for example, that we want to solve. Let's say 5 to the 7 minus 3x plus 9 is equal to, let's say 12, for example. Okay, here is an exponential equation. Okay, so the first thing we want to do with this exponential equation is we would like to try to isolate the exponential. That's this piece right here, the 5 to the power of 7 minus 3x. I would like this piece to be isolated on one side. So the first thing you're going to want to do here is subtract 9 from both sides. So we'll have that 5 to the power of 7 minus 3x is going to be equal to 12 minus 9. What is that, 3? Okay. So from here, you could take log base 5 of both sides, because log base 5 is the inverse of an exponential with base 5. But you don't have to. Natural log and log rule 3 kind of make up for that. So we're just going to use natural log. It's very common that pretty much every math textbook says, we don't need all these logs, why don't we just use natural log? Okay, we can bring the 7 minus 3x out front. So 7 minus 3x times the natural log of 5 will be equal to the natural log of 3. Okay. From here we want to solve for x. So let's go ahead and divide both sides by the natural log of 5. So we'll have that 7 minus 3x is going to be equal to the natural log of 3 all over the natural log of 5. Okay, we said, subtract 7 from both sides. So we'll get that negative 3x is equal to the natural log of 3 all over the natural log of 5 minus 7. Minus 7. And then we can multiply both sides by negative 1/3. Okay, so we'll move this up over here. So we have that x is going to be equal to negative 1/3, negative 1/3 times the natural log of 3 over the natural log of 5 minus 7. Okay, now we have a calculator exercise. This is the exact answer. This is the exact value. If the book or the WAMAP exercise asks you for the exact answer, this is exactly what you'll type in. If it wants an approximate answer, we'll use our calculator. Okay, so let's do it. So negative 1/3 times, what do we have? The natural log of 3 divided by the natural log of 5 minus 7, close the parenthesis, hit enter. This is what I have typed into my calculator. Okay, and we're getting, for rounding to 3 decimal places, 2.1057, so 106. So this is the approximate answer. Okay, what's a great way to check our answer? Well, why don't we plug this back in for x? Let's see if it works. So let's do 5. Let's go 5 to the power of 7 minus 2.106. 3 times that, so times 3. Close that parenthesis, and then we'll add 9. If we hit enter, we should get roughly 12, which we do. Notice I'm off a little bit because this answer here is rounded. But that's a great way to check your work. Beautiful. Okay, I'll go ahead and erase what I have here. Okay, so for these examples here, that I've just shown you, we've only had one exponential. There could be multiple exponentials. So let me show you what I mean. As our next example, let's say we have 7 to the x plus 1 is equal to 5 to the power of 1 minus 2x. So here we have another exponential equation that we want to solve. Go ahead and pause the video and maybe try this out on your own before we do it together. Okay, let's do it. So in this case here, there are 2 exponentials. And in our list, it said that we need to have them isolated on one side. Well, what's nice about this example is at least I have a single exponential on one side and a single exponential on the other side. There's no plus, no minus, something, or multiplication going on. So these, I have an exponential isolated on each side. So what are we going to do? Well, now we're ready to take the natural log of both sides. What do we want? We would really like for these variables to get out of the exponents. So first step, we're going to take the natural log of both sides. And you could use log base 10 if you'd like. It's very common just to use natural log. Okay, the x plus 1 will come out front, so we get x plus 1. We'll get the times the natural log of 7 will be equal to a 1 minus 2x times the natural log of 5. Okay, now we need to solve for x. And this can be a slightly tricky algebra problem. Now what's different about this one compared to the last two examples is that I have multiple x's and they're on both sides of the equation. So what do we want to do whenever we have a situation where we have multiple variables? We want to take all those variables, we want to bring them to one side of the equation, we want to take all the other junk and we want to move it to the other side. That's what we want to do here. So to be able to move all the x pieces to one side, we need to free these x's of this multiplication. We need to get them out of these parentheses so I can freely move them around. So what I'm going to do from here is I'm going to distribute in this natural log of 7 into these parentheses, and I'm going to distribute this natural log of 5 into these parentheses. So we'll have x times the natural log of 7 plus the natural log of 7. That's going to be equal to the natural log of 5 minus 2x times the natural log of 5. So I've distributed in the natural log of 7 and the natural log of 5. That's great because now I have these terms that just have x's in them and I can freely move them around. So we're going to go ahead and sniff out the x terms. Smells like x. Ooh, no, no. Oh, no. Yes. Has the right scent to it. Has the right scent to it. It's got an x in it. All of those pieces I want to bring to one side of the equation. Now it doesn't matter if you bring all this blue to the left side or to the right side. It doesn't make any difference. Let's bring them all to the left-hand side because I'd be adding this, and that's just an extra, an extra negative I don't have to worry about. So I'm going to write this as, we'll have x times the natural log of 7. I'm going to add 2x times the natural log of 5 to both sides, so we'll get plus 2x times the natural log of 5, and that's going to be equal to the natural log of 5. I'm going to subtract that to the other side, minus the natural log of 7. Okay. What can we do from here? Well, why did we want all our x's on one side? This is really a similar strategy to when we were trying to find the inverses of rational functions. The reason we like all our x's on one side is because we can factor out an x from each term. So factoring out this x, we're going to be left with, what? The natural log of 7. The natural log of 7 plus 2 times the natural log of 5 is going to be equal to the natural log of 5 minus the natural log of 7. Okay. We could finish the job by dividing both sides by the natural log of 7 plus 2 times the natural log of 5. Now, you don't have to do this next step, but I just think it's going to make everything look a lot nicer. I have all these natural log or log pieces together that are being added, subtracted, multiplied by numbers. You can use log rules to clean this up. So I'm going to choose to do that just to make it look nicer. So this is natural log of 7. What is this right here? This is the same thing as the natural log of 5 squared. I hope you believe. This is the natural log of 5 squared. I'm going to take the natural log of 7 plus the natural log of 5 squared, where the log rule allows us to multiply those together. So this is the same thing as x times the natural log of whatever 7. 5 squared is 25. 5 squared is 25. What's 7 times 25? What's 7 times 25? Well, let's see. I think it's 175. So this is the natural log of 175. Of 175. Okay, what do we have over here? Well, these logs are being subtracted so we can divide. So this is the natural log of 5/7. Okay. So now we can finish the job just by dividing both sides by the natural log of 175. So up here, I'm going to write the solution. We have that our solution, x, will be the natural log of 5/7 divided by the natural log of 175. And this is our exact answer. But let's go ahead and find the approximate answer. Grab my calculator right here. Okay, so what is it? So we have the natural log of 5/7 divided by the natural log of 175. So if you want to see, this is what I've typed into my calculator. Okay, let's go ahead and enter. So we have that x is approximately equal to negative 0.0. If we're rounding to 3 decimal places, it'll be 6.5. So this is the approximate answer. Beautiful. Okay. Let's have you try one let's have you try one in this flavor. Okay. Try. This is a try problem. Okay. Let's say we want to solve. How about 5 to the power of 1 minus x is equal to how about 6? How about 6 to the 3x plus 2? Go ahead and pause the video and try to solve this exponential equation. Okay, let's do it. We have exponentials isolated on both sides. What can we do? We're going to take the natural log of both sides. We want to get those variables out of the exponents. And that's what logs allow us to do. So we'll bring the 1 minus x out front. Don't forget these parentheses. This is going to be equal to a 3x plus 2 times the natural log of 6. Okay, let's distribute in the natural log of 5, and let's distribute in this natural log of 6. So we'll get the natural log of 5 minus x times the natural log of 5. And that's going to be equal to 3x times the natural log of 6 plus 2 times the natural log of 6. Okay. What we want to do from here is we want to isolate all our terms that have x's in them. So, nope. Yep. Yep. Oh, no. Okay. You could bring all the blue to the left. You could bring it to the right. Doesn't really matter. I'm going to go ahead and bring them to the right because, I don't know, I don't like negatives. So I'm going to add x times the natural log of 5 to both sides. So I'm going to bring all the x's to the right-hand side. So this is 3x times the natural log of 6. I'm going to add this plus x times the natural log of 5. Okay, we had a natural log of 5 here, and I'm going to subtract the 2 times the natural log of 6. So I put all my x terms on the right-hand side, and I have my non-x pieces on the left-hand side. Okay, why was this so great? Because now that I have my x terms on one side, I can factor out the common x. So factoring out that x, we'll be left with 3 times the natural log of 6 plus the natural log of 5. Okay, and over here we'll have the same thing. Let's clean up this left-hand side with log rules. Let's see, what would this be? This is going to be the same thing. Well, this right here is the same thing as natural log of 6 squared. So this is the same thing as the natural log of 6 squared, or this is the natural log of 36. So we have the natural log of 5 minus the natural log of 36. This is the same thing as the natural log of 5 divided by 36. Okay, we can clean up the right-hand side too. So what do we have? We have the natural log of 5 over 36. That's going to be equal to x. Well, we have 6 cubed. 6 cubed. What is it? That's a 6 times 6, so that's 36 times an extra 6. So what is that? I'm terrible at multiplying things in my head. So 6 times 30, what is that? 180 plus an extra 36. So what is that? 100. What is it? 200. 226. I don't know. I'm trying to do that in my head. Is that what 6 cubed is? 6 cubed. 216. 216. 216. 216. Ah, well, Yeah, 216. Yeah, there we go. 216. Okay. So we have what? So we're gonna have 216. This is the natural log of 216 times 5. So this will be the natural log of 216 times 5. I'm not gonna do that in my head. So 216 times 5, that's 1080. 1080. Okay. So we can solve for x by dividing both sides by the natural log of 1080. So we have x is equal to the natural log of 5 over 36 all over the natural log of 1080. And what are we going to get here? Let's see. So we have the natural log. So I guess I should say that this is the exact answer. This is the exact answer. The natural log of 5 divided by 36 divided by the natural log of 1080. Let's see what we get. I'm getting roughly negative 0.283 if we're rounding to 3 decimal places. Okay, let's check our answer. So let's see. What if we have a 5 to the power of 1 minus a negative 0.283. Okay, and is that the same thing as doing 6 to the power of 3 times a negative 0.283? What, plus 2? Yeah, I'm getting roughly 7.88 for both of them. So yes, this would be the correct answer here. Okay, so if you want to know what I plugged into my calculator, I was checking that when I plug in roughly negative 0.283 into the above equation, both sides were roughly getting the same answer. Of course, I rounded a little bit, so that's why it's a little bit off. But yeah, this would be the right answer. Okay, let's do another fun exercise. Let's go ahead and erase what we have here. Let's do a problem. Let's do a problem where we have money sitting in a bank account. We want to know how long it takes to accumulate to a certain number. So let's say we put, so as our example, let's say we invest, so our principal, let's say we invest, I don't know, how about 8 grand? 8 grand into a bank account. Let's say that our interest rate is, I don't know, let's say it's 6%. Let's say we get a 6% annual interest rate. Let's say that we are compounding, I don't know, let's say we're compounding monthly, so N would be 12. So this is our bank account. The question is, maybe we're saving up for that Lamborghini. How long till we have, I don't know, $500,000? How long would this take us? Well, let's set this up. What would our bank account look like? Well, we put in 8 grand. Okay, so we'd have 1 plus, our interest rate is 0.06. So a 6% interest rate, we're cutting that into 12 pieces, and we would be compounding 12 times a year. So here is a function that tells us how much money we're going to have in our bank account after 2 years. Now the big question is how long, what value of t, how much time would it take for this bank account to accumulate to $500,000? Go ahead and pause the video and give this a shot on your own. Solve for t. All right, let's do it. Let's move this up here. Let's put this up here. So we have $500,000. We put 8 grand in a bank account. 1 plus 0.06 over 12 to the 12t. Okay, we want to solve for t. Okay. what is the first thing we need to do here? The first thing we need to do is isolate the exponential. So we are going to go ahead and divide both sides by 8,000. Notice our exponential is the 1 plus 0.06 over 12 to the power of 12t. This is our exponential. This is the piece we need to isolate. So let's divide both sides by 8,000. So we'll have 500,000 divided by 8,000. 1 plus 0.06 over 12 to the 12t. Okay. Let's see, what can we do on the left-hand side here? I can get rid of a bunch of zeros. We can get rid of 3 zeros. So it's the same as 500 over 8. 500 over 8. So 500 over 8. Okay. Now what do we want to do to both sides? Well, I want to get this t out of this exponent, so we're going to take the natural log of both sides. So let's take the natural log of both sides. Okay? So we'll have the natural log of 500 divided by 8. That's going to be equal to what? 12t times the natural log of 1 plus 0.06 over 12. Okay, the 12t moved out front. And now we want to solve for t here, and we can do that by dividing both sides. Well, what's being multiplied onto t? Well, a 12 is being multiplied onto t, but also a natural log of 1 plus 0.06 over 12 is being multiplied onto t. Okay, so these would cancel. And we'd have that t will just be equal to the natural log of 500 over 8 all over 12 times the natural log of 1 plus 0.06 over 12. Okay, let's plug this into our calculator. What do we get? So we'll get the natural log of 500 divided by 8 divided by, I need to make sure to put this whole denominator in parentheses when you're plugging this into your calculator. So divided by in parentheses, we'll have 12 times the natural log of 1 plus 0.06 divided by 12. Okay, and I'm getting that t is equal to 69.0, we'll say 092 years. So you just gotta wait like 70 years. Hey, but you know, we'll get there, you know. So it'll take you 70 years. So you may want to start out with more than 8 grand in your bank if you want to, you know, not wait this long. But this is a great way. To figure out how long it would take you for your 8 grand to grow to $500,000. What's a great way to check our answer? Let's plug it in. If we have 8,000 times 1 plus 0.06 divided by 12, okay, to the power of, put parentheses, 12 times 69.092. So I should put years here if we're thinking about units. Okay, and take a look. We're getting roughly $500,000 here. Of course, the error is coming from rounding, but this is roughly how long it'll take. Okay, fun. Okay, what I'd like to do here is just show you some other kind of flavors of exponential equations that we may need to be aware of. Sometimes we could have exponential equations that are what we call quadratic in form. So let me show you an example. Okay. So these are kind of called quadratic type. Okay, let's say for example that we have e to the 2x minus e to the x minus 6 is equal to 0. Let's say we want to solve this type of equation here. Go ahead and pause the video and maybe try to think about this one here for a second before we do it together. Okay, let's do it. This equation, like the title says, it's a quadratic type, or it's quadratic in form. Well, the way we want to see this is the same thing as e to the x quantity squared minus an e to the x minus 6 is equal to 0. Just another way to write this. What we can do here is we can make a substitution. How about we let y equal e to the x? And this way we can hopefully see this a little bit better as a quadratic. If we make that replacement, e to the x's will replace with y's, so we'll get that y squared minus y minus 6 will be equal to 0. This is now a quadratic that we can solve. Okay, so how will this factor? This will factor to, let's see, I think I need a combination of 3 and 2. And you need to add to a negative, so the bigger of the numbers has to be negative. Okay, so I hope you see that this is screaming at you that y needs to be 3, or that y needs to be negative 2. Okay, well, we're not trying to solve for y here. Remember, we're trying to solve for x, and now remember that y is the same thing as e to the x. Okay, so we have two separate equations we need to solve here. So I need to figure out when is e to the x equal to 3, and when is e to the x equal to negative 2. We need to solve both of these equations. Okay, let's think about these. I'm going to erase what we have up here, give ourselves a little bit more room. So this equation comes down to us trying to figure out when is e to the x equal to 3, and when is e to the x equal to negative 2. Okay, so how are we going to solve these? We're going to take the natural log of both sides. So let's go ahead and take the natural log of both sides. We'll do this first one here. Okay, well, you could think of this in two different ways. One way you could think about it is that the e to the x and natural log, this is just log base e, they're inverses of one another, so they just cancel each other out. So this is just saying that x is equal to the natural log of 3, or just switch to exponential form. This is saying, if we switch to exponential form, this is log base e of 3 equals x. Really remember switching to exponential form is really just switching forms is, log form and exponential form is just a shortcut for applying the inverse function to both sides. If you didn't like me doing this here really quick, this x could come out front. You could think of it, log rule 3. This says that x times the natural log of e is equal to the natural log of 3. But what's natural log of e? This is log base e of e. This is saying e to what power gives you e. I hope you believe that e to the first gives you e. So this is just saying x times 1 equals the natural log of 3, or that x is the natural log of 3. So there's a couple different ways you could think about this. But either way, we get x is equal to the natural log of 3. Okay, we can plug that in our calculator to figure out roughly what that is. This is the exact answer. But what is the natural log of 3 approximately equal to? So the natural log of 3 looks like it's roughly 1.099 if we're rounding to 3 decimal places. Okay, let's try to do this next one. Okay, let's take the natural log of both sides. Okay, so here again, you can think that the natural log and e, these are inverse functions of one another. They just cancel each other out. So this says that x would be equal to the natural log of negative 2. Let's try to plug this into our calculator. Okay, so if we're doing the natural log of negative 2, beep, 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 error, 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 we're getting an error. Why are we getting an error? Why are we getting an error? Oh yeah, we can't take logs of negatives or 0. Negative 2 is not in the domain of the natural log. Thou shalt not take natural logs of negatives or 0. This doesn't make sense. There is no solution for this piece. Now, you could see this by taking the natural log of both sides, or we could think about this graphically. Of course, e to the x could never be equal to negative 2. Of course this doesn't make sense. What does the graph of e to the x look like? That's an exponential function. That's an exponential function. That's an exponential function. Okay, what's true about exponential functions? Well, ones that haven't been transformed, they're always above the x-axis. They only spit out things strictly bigger than 0. Of course, there's no output that gives you -2. That's another reason why you can't take natural logs of negatives. Okay, so we have our solution. We have to check these. This is not a right answer. We only have one answer to this equation, and that's x, which is equal to the natural log of 3. This is the exact answer. This is the approximate answer. Okay. Okay. Let's have you try one of this flavor. Let's have you try one of this flavor. Okay. So try the following. Let's say we have 9 to the 2x minus 3 times 9 to the x minus 18 is equal to 0. Go ahead and pause the video and give this a shot. Okay, let's do it. Let's do it. The thing we need to notice here is this is 9 to the x, all being squared, minus a 3 times a 9 to the x. Remember, this is not 3 times. This is a common mistake I see students make. They think it's 3 times 9 being raised to the power of x. They think this is 27 to the x. No. The exponents, a convention that we use for exponents, is the exponent and it only sees what's directly next to it. So this is 3 times 9 to the x. So be a little bit careful. Okay, let's make a replacement. Let's let y equal 9 to the x. So we have that y squared minus 3y minus 18 will be equal to 0. I think we can factor this. If not, you'd have to use the quadratic equation. Okay, so y. Let's see, I need something to multiply to 18. I think I need a 6 and a 3. One of them has to be negative. The bigger has to be negative. Okay, so this is saying that y could be equal to 6, or y could be equal to -3. But remember, we're not trying to solve for y, we're trying to solve for x. So we would have that 9 to the x would be equal to 6. Or we would have 9 to the x would be equal to -3. I hope you believe that right off the bat, that this doesn't make sense. 9 to the x, that's an exponential function. It's always above the x-axis. This one doesn't make sense. You try to take the natural log of both sides. If you're taking the natural log of -3, that's a no-no. That's a no-no. So the only thing we can do, the only one that's going to make sense is us solving 9 to the x equals 6. Okay, let's do that. Okay, so we need to solve 9 to the x equals 6. Okay, you could take log base 9 of both sides and use a change of base formula. It's going to be easier, I think, just easier for me to remember to take the natural log of both sides. So that x will come out front. So x will be equal to, x times the natural log of 9 will be equal to the natural log of 6. We can divide both sides by the natural log of 9. So x will be equal to the natural log of 6 over the natural log of 9. We can now plug this into our calculator. So we have the natural log of 6 divided by the natural log of 9. I'm getting that this is roughly 0.815 for rounding to 3 decimal places here. Notice here, just for fun, that, if we had 9 to the x is equal to 6, we could have taken log base 9 of both sides. Okay, these are inverses, they cancel each other out. So x would be equal to log base 9 of 6, but this button's not on your calculator, so what would you do? You'd switch the base, and you'd say this is the natural log of 6 all over the natural log of 9, which is just exactly where we got to just taking the natural log of both sides. So either way would work. Okay. There is one more type of equation I want to solve for you. Let's say, for example, that we wanted to solve, let's say, 3x times e to the x, 3x times e to the x, plus an x squared times e to the x is equal to 0. We want to solve this equation here for 0. We want to solve this equation for x. Okay. This one here is a little bit tougher. It's a little bit tougher. How are we going to solve for x here? Well, what's nice when we have an equation and it's equal to 0, something to try to do is to try to factor this. Notice, for example, that both these terms have a common e to the x in them. We can factor out that e to the x, and we'll be left with, what, 3x plus... We can even factor out an x. We can factor out an e to the x and an x. E to the x and an x. And what are we going to be left with? We'll be left with, what, a 3 plus x will be equal to 0. Okay. Well, what can we do from here? Well, I have 3 things being multiplied to give me 0. So what does that mean? That means that one of these pieces has to be 0. So this is what's called the zero product property. This says if a times b is equal to 0, then either a is 0 or b equals 0. This would also be true for a times b times c equal to 0. This would mean that a would have to be 0, or b would have to be 0, or c would have to be 0. This would be the same thing if it was a times b times c times d equals 0. Hopefully this should make sense why this is true. If I have 2 numbers being multiplied to give you 0, well then one of them has to be 0. Try to think of any 2 non-zero numbers that multiply to give you 0. There are none. If you could think of any, you'd win like a great math prize. Okay, so what this says here is, well, either e to the x could be 0, we could also have that x could be 0, or we could have that 3 plus x could be 0. Okay, well, x equals 0 would be a solution. Hopefully you see here that x equals negative 3 would be a solution. But now we need to solve e to the x equals 0. So maybe if we're not thinking about it, we could just say, oh, I'll just take the natural log of both sides, which would be fine. Okay, well, these are inverses. They cancel each other out. So x would just be equal to the natural log of 0. Okay, let's attempt to plug this into our calculator. The natural log of 0. Hit enter. Error, 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 error. Why? We can't take the natural log of 0. That's a problem. Remember, we can't take the natural log of 0 or a negative number. Okay, so I'm not getting any solution from this piece. And again, we can think about why. What does the graph of e to the x look like? The graph of e to the x looks like this. Remember, it has a horizontal asymptote. There is no x value that gives you an output of 0. E to the x is always strictly above the x-axis. There is no solution to this piece. There are only 2 solutions, x equaling 0, and, x equaling 0, x equaling 0, and x equaling negative 3. So these are our only 2 solutions for this problem. Okay. Let's have you try one of this form. Okay, let's say we want to solve. I don't know. How about x squared times e to the 2x plus 2x times e to the 2x is equal to 8 times e to the 2x. Go ahead and pause the video and give this a shot on your own. All right, let's do it. The first thing I'm going to try to do here is, I'm trying to solve this. It's going to be nice if I have everything on one side. We're going to try to factor this if we can. So we have x squared times e to the 2x plus 2x plus 2x times e to the 2x minus 8 times e to the 2x will be equal to 0. Let's notice that we can factor out an e to the 2x. So we'll be left with what? An x squared plus a 2x minus 8. We can try and factor this. We get e to the 2x. What will this factor to? I think an x plus 4 and an x minus 2. will be equal to 0. Okay, so this says that either e to the 2x is equal to 0, or that x plus 4 equals 0, or that x minus 2 is equal to 0. So help me believe here, x would be equal to negative 4. Over here, x will be equal to 2. And over here, well, you could try to take the natural log of both sides. This is an exponential function. And this exponential function will always be above the x-axis. So you could hopefully realize that you're not going to get any solution to this if you forget that. Again, you could just take the natural log of both sides. So you get that 2x would be equal to the natural log of 0. But, we can't take the natural log of 0. So we're not going to get any solution from this piece. So the only solutions we have is x being negative 4 or x being 2. Okay. Those are all the examples I have for this section, at least for this part of this section. What we're going to be doing in the next section, is solving logarithmic equations rather than exponential equations. We'll see you there. Take care.